In the early decades of the 20th century, the discovery of something called antimatter raised a significant problem. This new substance called into question how our matter-filled universe could exist at all. Let me explain. In 1928, Paul Dirac came up with a new and elegant equation to describe how particles, like electrons, behave when they travel close to the speed of light. Surprisingly, Dirac found that his equation always had two solutions, sort of how the square root of a positive number always has two answers. Dirac recognized that one solution described the electron, but the other, well, that was a mystery which he first dismissed as a mathematical artifact. He later said it took him 3 tortured years to summon the courage to claim that this other set of solutions was describing something real, antimatter. That is, the first solution described an electron, while the second described an anti-electron. The anti-electron would have the same mass and spin as the electron, but it would have an opposite electric charge. Now, since the electron has a negative charge, the anti-electron would have a positive charge, which is why we also call it a positron. Dirac's equation says the same thing is true for all particles. Quarks have antiquarks, and just as quarks can make up protons, antiquarks can make up antiprotons, and antiprotons and anti-electrons, they can make anti-atoms, and so on. Dirac's theory was a remarkable achievement. If proven correct, it would double the number of known particles in the world. Just 4 years later, in 1932, Carl Anderson took this picture of a particle racing through a bubble chamber. His measurements showed that it had the same mass as an electron, but a positive electric charge, the first detection of antimatter, verifying Dirac's mathematical prediction. Now we come to the puzzle. When matter and antimatter come together, they annihilate. And this raises a big question. Why is there any matter left? After all, if matter and antimatter are identical except for having opposite electric charge, and since as far as we can tell, the laws of physics don't have a preference for a plus sign over a minus sign, we would expect equal amounts of matter and antimatter to be created at the Big Bang. And then, as they intermingled, the matter and antimatter would all annihilate, leaving a sea of structureless radiation. But if this were the case, the universe as we know it wouldn't exist. So what's going on? Physicists have been puzzling about this for more than half a century. Some have wondered whether the antimatter got separated from matter and might still be out there, existing as anti-planets, anti-stars, anti-galaxies, maybe even anti-universes. Others have imagined that just after the Big Bang, a tiny imbalance between matter and antimatter somehow crept in. Indeed, to avoid total annihilation, scientists have calculated that for every billion antiprotons, there must have been a billion plus 1 protons. That's a tiny imbalance, but it would have left over just enough matter to make all we see in the universe today. To figure out which, if any of these theories might be right, scientists are undertaking a range of experiments to understand antimatter with far greater precision. And all this is part of a grand quest to answer a question that is as simple as it is profound. Given that matter and antimatter annihilate, how is it that we exist?